Okay, so as many other demo today, I'm going to jungle between PowerPoint, terminal, and the tutorial on TEHUB. So basically, actually, after this very nice presentation, and I should say that this work, dnaPipeTE, you're going to find a lot of similarity with Repeat Explorer, and it's for a good reason. It's because I actually learned bioinformatics by using Repeat Explorer, and I had really this need of finding repeats in a species with no genome. Of course, it was a time in the past, but it can still happen. But also, the purpose of this tool, and maybe a distinction, is that the one aim is really comparative genomics, and to run in parallel many samples of the same species or related species to compare their TE content. And so I'm gonna do a very brief introduction of what is dnaPipeTE and how it works. And then we will attempt to do a demo of a normal run and look at the main output. And of course, it's going to be too long for the time. So I will be very happy to have you asking me, sending me emails, or talking to me right after. So to follow the tutorial, it's like everything else on the TEHUB, and there will also be data sets that we're going to download at the beginning in order to get the output if we don't have the time to do it all. So dnaPipeTE is really similar in the concept with Repeat Explorer. The idea being, if you take some short reads on the genome, or you can take an assembly and chop it into pieces, actually simulate short reads, and that you subsample under 1x, you and attempt to assemble these reads, you are going to principally assemble things that come from repeats. And that's good, because that's what we want. And from the proportion of repeats that you find in your sample, you can infer what is the proportion of repeat in your genome. And Peter was talking about an advantage of starting from short reads or from reads before assembly is that indeed you may miss sometimes stuff in assemblies, and you might want to also compare what happened if you start from short reads or reads, and what happened if you start from your assembly. So a few examples of how it is used. Sometimes it's used actually in complementation or in parallel with Repeat Explorer to compare through different methods whether you end up with the same result or not, which can be interesting. So of course I took an example where it's 8 match. So it's used to estimate the repeat content in one species or a couple of species. Like you see here, it's been used in some study where the total repeat content is studied in correlation with the genome size to understand what happened in the genome that become big and bigger and bigger. And one aspect that is also often used by the dnaPipeTE user is because it has the ability from the short reads to create or to estimate repeat landscape. It's not the same, it doesn't have the same precision than a repeat landscape that you can make after using a repeat masker on an assembled genome, but it gives you a little idea of what's going on with the repeat in your genome and what is their dynamics. So the data requirement is quite simple, and at the minimum, you just need short reads, and actually we only use one end of the reads for this analysis. The paired end is actually not used, and also it can be creating some chimerical things if you are like on the boundaries of T, or you have T into T. So I just didn't want to deal with that, and I said, no, I'm not going to do it. So it's a single end. And if you want to estimate also the relative proportion of the different type of T, and you happen to have a T library, or you want to try to infer it from homology from other libraries, you can provide a T library. We will see it's in the format of repeat masker that we're starting to be used to it today. And as it was also mentioned before, for this type of approach, it's better if you have some estimate of your genome size, because when you want to compare different species, for example, it's just a little bit better to know what is the variation in genome size when you're going to see variation, then also in T proportion. Even though we always work with proportion, it's a safe control. So the pipeline, the way it works is like 4 main steps. The first is a sampling of your raw reads. So you can just take your data from the sequencer. Ideally, you do a little bit of QC on it. And I'll talk a tiny bit more about it, but we won't have the time to do that today. Then the second step is to assemble this repeat. And for that, we hijack another software that is not made for it. That's actually made to assemble RNA-seq. But it's the same idea, because in RNA-seq, the more a gene is expressed, the more it has reads, so the better you're going to assemble it. And here, the more a TES copies in the genome, the more it's going to have reads in your sample, and the better you're going to assemble it. So we do this assembly, and from this assembly, we are going to extract our counting and try to classify them using repeat masker. And if each counting passes a threshold of annotation, we're going to move on to the quantification step, where we're going to map the read against this counting, and just to quantify, to count how many times, how abundant each counting is in the genome. So for the tutorial today, we are going to work only on this part here on the right, but I'm going to talk quickly of what you can do first. Is so you get your short reads, you can get them from your experiment or from public databases. Usually you would do a little bit of QC, quality trimming, and also it's recommended to filter organelles like the mitochondrial DNA, for example, that if you don't remove it, it will show up as one of the most abundant repeats. And also if you know that you have very large gene family, like sometimes odorant receptors or things like that, that tends to explode in quantity. Some users have reported that it ends up in their outputs. So you can also try to map them out of your read before. And so for this tutorial, we are going to use one-end reads that I had prepared for that. That it's a 2x data set that it's supposed to represent the full data set. We're going to put it in dnaPipeTE, and from the output, we're going to use two little scripts that I recently added to the distribution to process or reprocess, because it starts to be a bit old, and I was not very happy with the way it was looking. So we are going to make some summary charts and look also at how to create TE landscapes. So we are going to skip the installation. That's the beauty of these sessions, is that you don't have to think about that. But if you want to do that, we recently simplified the whole process by integrating it into in a Docker container that you can also use with Singularity. And the documentation is fully available on GitHub, plus this tutorial is on the TEHUB. The data we're going to use today are short reads from Drosophila melanogaster, of the actual original strain that is sequenced for the reference genome. So that gives us a little bit of comparison. And as I was saying before, I have already removed the mitochondrial DNA, so that's going to let us try to save some time. So something a bit critical in dnaPipeTE is if you want to have a nice classification, and I have to insist that it's never going to be an extremely good classification unless you know already the T, which is not the point of this thing, right? So it's you are going to try to annotate only by homology, because we are using repeat masker, but it's already a start. It gives us a little idea, and you can see that it can be quite useful already. So I put some information here. We don't have to do that right now, but if you want to use either extract data from DFAM or get the data from RepBase, you have different ways. The only thing that matters is that it looks like this, the format that we have been talking many times today. So I think you should be familiar now. Otherwise, you just ask Jessica. Okay, so we are going to start the hands-on tutorial now. I'm going to hope that there's no problem, but why? So the first thing we are going to do is create a project folder in the home directory. And we are going to download the data, so the input data, the T library, and also the results. So we can cheat and just do a fake run and look at the results. So let's go. You can, of course, copy and paste from the tutorial here. So we can move on here. We are going to do all that. It might be dangerous to copy all at once. Do you see properly the terminal? Is it okay? I can make it a bit bigger. All right. And you don't see the bottom, right? So I'm going to. Okay. So we create the project folder. And we go in home projects. We look, okay, there's nothing. So we are going to now download the data that I have stored on this little repository here. I use wget. Some people use curl. I think you do what you want. Let's see if when we all download at the same time, if we make the VM explode or the internet connection. All right, so let's continue and let's extract our data. I'm gonna try to go a bit faster. And I'm gonna, it's extracted. I'm gonna already remove the archive. Okay, so I don't have tree installed, I think, in the VM, but this is how the folder structure is going to be. We are in home/project. Within this directory, we have a data directory that contains our T library, that is drozot.fasta, that I had extracted from the FAM. And we have some short reads. It's the R1, it's 2x here. And we have the magic folder with the result. So to run the dnaPipeTE, we have to launch and to get inside the container. And we are going to use this command here. So run -it. IT means interactive. So it means that you are going to be like you've done today, actually, within the container, like if you had a machine within a machine. And what's important to note here is that we are going to bind also the project folder that we have on the virtual machine that actually should, in normal cases, will be your own machine. And we are going to say, hey, actually, I have an image for that. We're going to say, hey, we are in the VM here, and we have the project folder with data inside. And this project folder is going to be equal to the mont folder in the Docker. So when we are going to be in the Docker container, we will use mont instead of project. But then what's behind it, data, is going to come after you're going to see it. So we launch this, and the prompt changes here to tell us that we are in the dnaPipeTE. We're actually in a specific folder that is the right one, so don't go around. And if I do ls of /mont or mnt, I should see data and dnaPipeTE tutorial result. So this is our folder. It worked. Perfect. So what do we do next? We are going to actually launch the program. And on the tutorial, there is a normal run that is with a normal average coverage. And actually, I'm not going to have the time to discuss what is the most appropriate coverage, because actually it's never the same. It depends on your species. But very, very soon, there's going to be a paper that describes all this procedure. And so I would be very happy to share that with you. And actually, I can later discuss it with you, of course. So for this analysis, what actually on the tutorial page is what we want to really do is like 2 Trinity iterations means we are going to do the assembly twice, and I'm going to show you when it runs why we do that. And we are going to use 0.15x, so only 15% of 1 time the genome. And I tell you it creates config of repeats, and to know what type of repeat it is, we use repeat masker, but we are going to put a cutoff on how much the query should be covered by an annotation to keep it. Because once we annotate, we're going to infer from this whole thing that it's this type of repeat. So you want to be sometimes more conservative, sometimes you want to be more sensitive. So this is the 3 parameters that are the most important. And for the test, you can go on the tab that says Uppsala and copy the command where we cheated here and we put only 5x coverage just to go fast. And just for the fun to look how the output are showing up. So it's starting. And so the first step is the sampling. So we see it happening. It's pretty quick because it's not a lot of reads that we are doing to sample here. I'm going to show you here in the presentation what are these steps. I had actually prepared a slide on how to choose the best coverage, but I think I'm going to skip that for now. We can talk about it if we have time. The next step after sampling the read is sending the first batch of read to Trinity. So Trinity is going to try to assemble them, and if your reads belong to a repeat, they are going to be assembled into a config. If they come from a non-repetitive region, it's very unlikely that they are going to find another read to be assembled with, and they should be not assembled. So why do we do 2 runs of Trinity? It's because we want to enrich our reads in repeats to try to improve a little bit the quality of the assembly. So what we do is after the first run, the reads that have contributed to this first config are merged with the second sample that we are doing. So if the first sample was 0.15x, the second sample is going to be somewhere between 0.15 and 0.30x, and should be enriched in repeats. So we do that again. Usually 2 iterations are enough, but of course you can try as much as you want. The next step is to take our assembly, and repeat masker is going to do it. We can actually look if it's doing it. No, it's still assembling right now. So after the assembly, it goes to repeat masker. You've seen repeat masker today, so no need to describe that more. But according to a threshold, we're gonna keep the notation, and I will show you how it is in the output. Then it's gonna do things that some are useful, some are not useful anymore, really. That's the steps that I put with fossil here, because they're just fossilized in the Docker. You know, this pipeline is probably 6-year-old, and try to remove too much things, it can break, and I just didn't want to do that. Maybe I was a bit too lazy. So the quantification is done by BLAST in order to be sensitive enough from short reads to be able to match only even small portion of reads to our config of repeats. And also from the BLAST, we're going to extract the divergence between the read and the contigs. And this is what we're going to use to make our read landscape. No, T landscape, sorry. Okay, so let's checkpoint what's going on here. We are still in the assembly. Does any of you are trying and it's running, or have you even finished the assembly? Or? It doesn't matter, actually. So you can leave it run, no problem, just so you can explore yourself the output. But we don't have to do that. We can just send him a big Control-C to tell him to, okay, it's okay. And we are going to actually look at the output in the folder with the real output. So what we can do at that point, yes, because we're going to do some post-processing later. Let's stay in the Docker, but you could do the same from exiting the Docker. It's going to be in your project folder. If I do ls of mount here, I see that I have data, dnaPipeTE mock. That's the folder we have created with our in the test run. But we have this dnaPipeTE tutorial results that are here, and so we can ls this folder to list this folder what we have there. Wow, many files actually, and so it's like many. It's way too much actually, but I'm going to show you what's really interesting here. So the first file you might really want to look at is the trinity.fasta. This is the actual assembly. We can do this. No, we cannot, because I'm not. I'm going to go directly in the folder. Sorry. Okay. All right. So this is a multi-fasta. With the nomenclature of Trinity. Once again, I don't really have too much time to describe what is the nomenclature, but in the tutorial, there's like a little blurb about it, and there's also a link with the Trinity documentation that explains in details how Trinity assembles and name the different clusters. So we have, you can see many small clusters because it's expected we are at very low coverage. We don't expect to assemble all the repeats perfectly. Actually, the ones that are the most abundant are going to be the ones that are the best assembled, and etc. So, okay, we can look at it a little bit. Pretty cool. Then we have the raw output from repeat masker that we can take a quick look at it. So, sorry, it's a bit here, but basically you have each config and each annotation. In actually, if you look, there is a folder called annotation, and if we do a little ls in annotation and we look at this one RM hit per Trinity contigs, it is what it is, what it says actually, and it's basically it's a sort of it takes the best hit for each config, the best hit of repeat masker. So you can tell, for example, okay, this config it has like a line, it's a line, etc., etc. Okay, yes, I'm going to, perfect. Oh, wow. Okay. So the second most important file, probably after the actual row assembly, is the quantification and classification merge, where it's well, I just should show you actually, that would be clear. So if you, oops, sorry. So in the main, we are still in the main output folder. You want to look at the file that's called reads per component and annotation. Components are the config of Trinity, basically. So it's a table like so, with actually, no, it looks like that, and then I'm going to show you with the annotation here. No, okay, there. All right, so this is the same table, and I just took the two first lines so we can see exactly what we have here. So the first column is the number of reads that have mapped to each config. The second column is the number of base pairs. So for example, if you have a read that maps, but only half of it, only 50 base pair match, it's going to be reported as 50 base pair. So you might have a little difference if you look at the proportion from reads or from base pair. It's up to you. The config name, the config length. So here we have assembled a 10 KB config with an annotation of R2 Drosophila melanogaster. It's a line R2, but if we look here, we see that the annotation proportion, meaning only 34% of our config is going to be covered by the hit. So if you think this is not enough for you to be confident, you can just increase the sensitivity, the threshold. It's RM_T that we have used to say, okay, I just want 40% just to be really sure that I'm not reporting wrong things. And the second one is actually a much better one. It's almost 8 KB, where almost all the sequence map is like annotated by root internal sequence. So we can assume that we have a good assembly of the root transposon here. Okay, so I'm sorry because it's running a lot. What do we want to do with that? Maybe this is enough for many people that you can just use this table in your downstream analysis. I wanted to be able to provide some visual outputs, and just for the sake of time, I'm not gonna do it interactively. You can do it if you want. The commands are here. We're gonna look at Uppsala because just the name is a bit different here. The first script is called dnaPipeTE charts, and you can call it directly from the when you are in the Docker container. It's in the path. It's gonna come in. There's no need to look for it. So it's here. And the input is going to be our output folder directly, right? And O is for the name of a prefix for your output. And it's going to automatically create a PDF file in your output folder. And if you bring it back to your laptop with a screen later, outside of your cluster or outside of wherever you use, actually it can run on a laptop with 8 cores and 10 gigs RAM, it can run. Drosophila melanogaster. So the first pie chart is the relative proportion, so the relative proportion of different type of repeats. The second is the relative proportion of repeat in the genome. So the Drosophilist experts will notice that it might not be as much as it is, or as exactly as we know from the assembly. We have to be sure that melanogaster is probably one of the most well-known and assembled genome, and we have the best repeats, so we are looking for perfection here. Usually we want to use this when we don't really know what's going on. If you increase a little bit the coverage, you can reach a sweet spot where you're gonna exactly match what you should find. And this graph is actually very similar to what Repeat Explorer produces, that quantify actually each in Repeat Explorer it's each cluster. Here it's each config, and you can see the proportion of the genome. So we can see that around a bit less than 20% of the genome is repetitive here. We have a big first cluster that represent config that represent more than 1.5% of our genome, etc. So okay, and then recently I put colors, so it's nice. And the I think quite cool part is that with just another little command, we can extract the divergence from our read to the contigs to create landscape. So T landscape represent the divergence. Well, ideally, it would represent the divergence between the copy and the consensus. Here, we don't have access to the copy, but just to short reads. So it's going to be the divergence between the reads that are going to be a proxy for the divergence of your family. The younger the family, the more reads you're going to find on the left here with 0 divergence, and the older the family, you're going to go there. And if you are used to Drosophila melanogaster, you're going to recognize this very specific landscape where most of the T are very recent, because in melanogaster, there's a lot of turnover. The genome deletes all the time. And the T, you can have specific explosion of family in some strain, not in others. It's very dynamic. But if you were to use a mammalian genome, you would see maybe something a bit more centered to the middle here with all Ts. You can actually choose whether you want the superfamily or the class, the subclass, different degree of specificity. And I think I'm reaching the end of my of the frog, and we're good, right? Yes, so I guess I don't know if I have time for questions, but I'm not gonna go far, and I'll be. Yeah, thank you.
I think maybe one quick question. If somebody has a burning, strong question they would like everybody to hear.
So it's a question that I have often. I have tried. There are several, I think, theoretical limited. I mean, you can do it. It would work. It would go through, right? Then I think we have to think of what's exactly happening with the quantification and the assembly. And I had thought for a while that it was correct, a good idea, and then I remember that I was not super satisfied. Yes, that's the thing, exactly, because you are looking at proportion and you try to estimate the proportion of repeat in your, that's the thing. You want to estimate the proportion of repeat from the more reads, the more it's repeated, so the more it's in the genome. And RNA-seq, the more it's expressed. So, I mean, I think you should try, or we should try, and see what's going to, technically, it can take it. So, yeah. Sorry, I cannot be more precise.